Okay, it's time to start. Welcome, everyone. Pleased to introduce myself. My name is Hermet. I'm one of the Tizen developer, specifically working for Tizen UI and graphics part in Samsung Research Center. Today, I'd like to talk a new approach to motion graphics UI with Lottie Animation. Perhaps some of you may have heard about Lottie Animation before. As you may know, Lottie Animation is one of the most promising animation methods for motion graphics. Actually, most platforms support this animation method for application UI. And this year, from Tizen 5.5, we also started support Lottie Animation. And I was involved in the project. And as an output, we created an additional open source project. The name is rlottie. So in this presentation, I'd like to talk briefly about the history of this project, how we started our Lottie project, and how we built our Lottie on Tizen, and what we've done until now for Lottie Animation, and what we are doing for further features. Okay, then let's get started. If you are not a visual interaction designer, you might be unclear or have no idea what exactly motion graphics is. Motion graphics is a sort of a computer graphics animation, like animation movies, video games, or UI effects. If there's some object or movie on the screens, and those screen scenes or frames were generated by computer processing, then that is the motion graphics. For the last 10 years, these motion graphics have been getting more and more used in UI world, and nowadays, it's one of the essential needs for better user experience. Obviously, if you look at the UI of your smartphone, it must be full of fancy animations. Even in smart TVs, watches, other types of devices as well. But, this animation effect is not just for eye candy. Obviously, it's functional and useful. In case of UI, this animation effect could provide clear feedback to users as the interaction effect. And also, it allows apps to save screen space so that apps could fulfill several functions simultaneously. Therefore, the users can practically understand each scenario context and functionalities more easily. But the thing is, in point of a development perspective, this motion graphics is likely to increase the burden of development. That means it actually much hard to code and design, requires more development resources. As a result, developers needed a better method for developing motion graphics or animation effect more quickly and more easily. But before moving on to Lottie solution, we are going to check how motion graphics works under the hood. To talk about this briefly, I'd like to separate motion graphics into two parts: frame controlling and rendering. Here, frame controlling means which animation source data we'd like to display with, and rendering indicates how we generate animation images using this animation source data. Let's assume that we already prepared a lot of animation source data. Then we need to select one of them at a certain time. And for this, we need to run sort of an animation loop which iterates 60 times per second as far as we support 60 FPS in a program. Similarly, this animation loop iterates continuously and prepares the animation source data for each loop and requests for drawing it. In general, this animation data is only available within a certain interval as a keyframe. Otherwise, there must be full of heavy animation data size. Thus, if there is no animation data at a certain frame time, we must generate it by interpolating between the previous and next existing data. And this animation data could contain the data such as timeline information, interpolation method, object properties, like the properties, image index, and some others. And we can use some basic or custom interpolation equation to interpolate these properties. By using this basic concept, we can actually control the animation frames on this animation loop to make a transition for motion graphics. That's what I talked about frame controlling. Then let's move on to rendering part. As I mentioned earlier, the rendering is a drawing job for generating the animation images. And actually, there are a lot of rendering methods. But in this case, we are just going to focus on vector graphics only. Vector graphics is a sort of a mathematical equation algorithm to draw all kinds of 2D shapes. In vector graphics, there are some traditional drawing commands, such as stroke, dash, path, fill, gradient, and so on. Generally, we can compose a shape using these commands. Moreover, we can compose a scene or model by mixing several shapes together. As you may know, one of the most famous vector graphics formats is SVG. Not like the past, this vector graphics is more used for modern app UI because vector graphics is available on the scalable resolution. Actually, vector graphics is able to generate full-size resolution images on runtime. That means applications don't need a set of various resolution images of the same content for supporting various displays. In other words, vector graphics use much less data of the content that brings application binary size reduction. On the other hand, these vector graphics may require more processing power than images if the scene or model is complex. But hopefully, these days, decent mobile machines are fairly sufficient to handle this computation in real time. Besides the UX trend, that's the one major fact why the vector graphics UI is more used than ever before. In case of Tizen, as you can see the right side, the Tizen UI graphics stack, Tizen provides each one vector graphics engine. Back in Tizen 2.4, the engine was introduced for supporting tiny SVG format so that it applied the vector drawings or UI control visuals. Then later, it had expanded to support the Lottie Animation. At the end, this vector graphics engine is integrated with rendering core to respond to commands requested and share the drawing output with rendering core. And here, rendering core is responsible for all kinds of drawing method, composition method, not only for vector output, but also for generic image drawing, font drawing, and some others. And to get this vector graphics engine working nicely with rendering core, we actually applied some basic, well-known optimization strategies, such as multi-threading rasterizer, themed instructions, and we applied a certain data compression method for drawing buffers. And also, we applied a caching mechanism case by case for more precisely for drawing buffers. For instance, we are not going to cache animated buffers, but to cache static or shadow buffers among the vector object. And also, we using shadow buffers to avoid the memory copy between the rendering core and vector graphics engine. Of course, Tizen supports the vector animation programming method. In Tizen, we can actually describe several stages of one vector object, and in those stages, we can describe some object properties, such as the shape, path, fill, stroke, color, gradient method, image index, and some others. And by switching this state with engine transition program, the engine could generate the animation result by incorporating these states inside of us. But the thing is, the numeric data over vector properties is not so intuitive to us. So perhaps we should construct a model from the vector data, such as SVG, to avoid the manual coding. But in this case, we'd rather design an engine to support the vector morphing mechanism for generating auto animation. But still, one problem is this vector morphing mechanism may have some limitation at a complex scene or model. It may sometimes it generate the different result than we expected. And even worse, if the animation has more than 2 stages, then the programmers must write the code to change the state case by case. That might be easy to bring the logical mistakes. As a result, we need a better method for this vector animation programming, and our choice was Lottie. As you may know, Lottie Animation is one of the vector-based animation methods. It was organized and introduced by Airbnb company. And the original idea came from the programmer, Hermet. He actually made an export plugin of After Effects to extract the animation source data from the After Effects tool, which is one of the most popular visual interaction design tools among the designers in the industry. And exporting the data from After Effects is a good point, since that tool is very professional and powerful. Already a lot of designers are used to it, and to continue to stick to further usages. Consequently, this Lottie Animation has been getting more popular in the industry now. And actually, more design tools are coming out supporting this Lottie Animation, not only native web, but also major platforms such as Android, iOS, Windows, even Tizen support this Lottie Animation. Therefore, the applications running on these platforms could use this animation method to make fancy aesthetic visual effects. Then, let's have a look at more details of Lottie Animation. This page shows an abstracted workflow of Lottie usage. Firstly, after designers finish the design in After Effects, then they can export the animation source data using body moving plugin of After Effects. And the body moving translates the After Effects internal animation source data to a sort of specified structure data using JSON format, and we can call this Lottie file. Now applications are ready for using this Lottie file as each one animation resources, but they might need a sort of Lottie player module, which simply consists of a Lottie file loader and Lottie render. And let's assume that this Lottie player is a static or X module library. Actually depends on the cases. Anyway, by using this Lottie player, application can play Lottie animation and control them based on application scenarios. But yet, applications might need a sort of a vector rasterizer to draw the Lottie animation. And as you figured out, Tizen case, we could understand the platforms basically support each one decent vector rasterizer. That means here Lottie player could request a platform to rasterize the Lottie animation frame images. Such applications could request the Lottie player to play Lottie animation and display each result on application screens. As you may know, After Effects has a lot of visual and functional components for VI effects. And as you can see, the behavior sample on the screen is a primitive component contains not only shapes, but also transition and a composition method. And designers practically design VI effects using these components together. There are a categorization through the Lottie visual and functional components. And I think the most items in the list are understandable by looking each names, but match, seventh in the list, might be a little bit strange name for you. But match is quite similar with masking method. It's quite useful and necessary by the designers. That's why I'm pointing out here. Specifically, the match is a layer that defines transparent areas of the layer or another layer. On alpha channel, often used as matte, but you can use matte better than alpha channel does. Just keep in mind, masking or match may require additional render buffers and require some another render stages on runtime processing. That means these two components would be a little bit expensive or very expensive if they are used many times in one Lottie animation. So if you can make the same design without these two components, then I recommend that you can design your design by avoiding these two components for better optimization performance. And next, merge shape passes together as its name suggests. But it's not such a recommended component either because it also requires complex logical computation on runtime. Even some platforms don't support this feature perfectly yet. At the last layer effect is a sort of filter effect of After Effects that provide color corrections, such as fill, tint to layers. I just pointed out just a few components in the list, but actually there are more specifications of Lottie visual and functional components. And I think you can visit the After Effects online site to check the documentation for more details later. Anyway, these components in the list are available as the After Effects layer and shape attribute list. And mostly they are directly mapping to the After Effects design component, and they are expected to be consistently described in Lottie files. And here, Lottie files, left side, is actually well organized in the structure, but the readability might not be satisfactory if you have no idea the meaning of keywords, because keywords are abbreviated. So to understand the Lottie files, actually you need to check the body moving project to see how these keywords used in the project. Anyway, once applications are ready for reading Lottie files, then Lottie player takes parsing, interpreting Lottie text, and transforming the text to an interpreted data structure that is designed for Lottie animation. And here, result data structure is quite similar with the original design structure in After Effects, because all design components are roughly going to convert to the data item of the animation structure. That means in the earlier design step, we can figure out how many design components will be transformed to the data structure item, and we can figure out how many component data will be processed and work in the program on the runtime. So it will be helpful for the optimized design if designers understand how expensive each component is. To support Lottie animation in Tizen, we suggest a new Lottie player library. The name is rlottie. Rlottie means render Lottie, that is inspired by RSVG project, which is for SVG rendering. Basically, rlottie does reading Lottie file and lexing, parsing, interpreting Lottie syntaxes, and transforming to an understandable single-graph data structure for Lottie scene render. Here, Lottie scene renderer is programmed to update all kinds of Lottie component properties by processing them at a given frame time. Then rlottie ultimately generates the Lottie animation frame images through its backend vector rasterizer that is originated from Tizen vector graphics engine. All in all, this library contains Lottie file loader, scene renderer, and vector rasterizer. And additionally, it contains a set of convenient API set for controlling Lottie animation. To some of the key features of rlottie, firstly, it's an open source, a standalone library that doesn't have any package dependencies. Thus, applications can easily contain this library symbol if it's necessary. Especially, it will be good if applications require the exactly same method across the platforms. Secondly, the output of Lottie animation, rlottie actually, is a simple RGBA bitmap data that is available for sharing with the requester. As I mentioned earlier, this rlottie contains each one vector rasterizer. That means it doesn't need to depend on any platform UI graphic system. So you can use the animation result data as an independent image source in your application or in your project. And for more advanced usage, this rlottie provides the animation result as a generic vector property list, such as shape path, gradient, path, stroke, dash, and some others. Though this interface is not recommended unless you fully understand the data structure and each format, but we are expecting the users can control the Lottie animation more precisely by using this interface method. And in case of Tizen, actually we are using this interface method for customizing Lottie animation for more dynamic transition effect. And we are going to check some working prototypes about this at the end of this presentation. And third, the task processing and rendering of rlottie support both synchronous and asynchronous way so that users can optionally choose either method. Actually, rlottie works based on its task scheduler, which is quite similar with a threading pool method. Lastly, this project is oriented to Linux world. It's already being used in Tizen, plus it's packaged to Debian and Fedora distros officially. And I guarantee you can easily build and port this library onto your platforms, such as Android, iOS, Windows, and some others. Now we can check the usage of rlottie in programming wise. Basically, rlottie provides a C++ interface and additional C language binding. And in this case, we are just going to focus on C++ interface. Anyway, as you can understand by the example, it actually describes one simple basic usage. Firstly, it creates the one Lottie animation instance by specifying a Lottie file name. Then for controlling Lottie animation, it calls some animation properties. Then lastly, it requests the rendering by giving a surface target. Then rlottie ultimately render and generate the animation images onto this given surface target so that you can use it as an image source on the next composition stage. And of course, we can create multiple Lottie animation instances for controlling and playing Lottie animation simultaneously. In this case, rlottie will aggressively share the internal Lottie data among the different instances for better optimization performance. Now, rlottie is inside Tizen as the Lottie player is integrated with rendering core directory. In the text, here rendering core has a role for canvas and drawing stuff. It's tightly communicating with lower graphics backend and the higher UI engine. And here UI engine provides native UI controls such as window, view, scroller, buttons, and some others. And upon this, Tizen sets a Tizen.NET runtime and Xamarin frameworks that exposing C# and Xamarin interfaces. And while this Xamarin, Azure Xamarin is a portal layer that guarantees the UI compatibility, Tizen applications can use the animation view of Xamarin form for Lottie animation. And while this animation view working through its module, it actually requires the UI engine to create a native UI control animation view and make it to play Lottie animation. After that, UI engine requests the rendering core to draw the Lottie frames. And as you figure out animation loop earlier in this presentation, we could understand that your rendering core is supposed to handle application process main loop. That means here rendering core requests the rlottie to load the Lottie file and update Lottie animation frames by giving a specific frame number. Then rlottie render Lottie animation frame images and returns to rendering core so that rendering core can compose it as with the main canvas buffer. And for sharing the drawing buffers, we actually use TBM buffers to update the pixels on the spot. That means it maps the surface buffers as the texture source that is directly uploaded to the graphics system, such as OpenGL and others. And as you may know, the TBM is a Tizen buffer management system is fundamentally similar with the dynamic texture of the easier surface that accesses the graphics memory directly by the requester. So here, TBM allows us for sharing the texture memory more safely among different processes and modules, such as compositor, graphics driver, server, and client. All in all, this integration method is applied to the native UI system, both EFL and Lottie in Tizen. And actually, for controlling back the properties of Lottie animation, we actually applied an alternative integration method, as you can see on the screen. In this way, rlottie returns the animation result as a generic vector command instead of frame images. Specifically, rlottie returns the list of vector properties, which is compatible with the rendering core vector drawing interfaces. Thus, rendering core gets the vector data of Lottie animation, then handles some rendering stuff internally, then returns and then transfer them to vector graphics engine to rasterize the Lottie animation frame images. The main purpose of this approach is that we actually have a benefit by the usable functions of the Tizen UI graphics system. But other than that, here UI engine can access a specific vector node or Lottie animation to change its properties through the rendering core. And actually, in case of Tizen, we apply this integration method additionally to customize the Lottie animation for a dynamic transition effect. Now, we are going to check some working prototypes later in this presentation. There are some practical use cases about Lottie learning on Tizen. The one representative case is Galaxy Watch series. Officially, that is the first adoption of Lottie learning on product. Since the Galaxy Watch, it applied the Lottie animation for better visual interaction effect. Not only for workout animation, but also for watch faces, better charging, and weather, and some notification effects were introduced with Lottie animation. In fact, before Lottie feature, the product UX was barely supported by VR effects. In some cases, they used the MP4 or GIF resources in a limited way. But in most cases, developers had to write the logics manually for VR effects. And if the VR effect is too complex, then actually developers felt like they hitting the wall. I mean, they actually have to compromise with the designers to ease the animation effect or abandon them. Thus, obviously, there are many complaints for developing VR effects in Tizen product, and now many cases were solved with a Lottie solution. Another showcase is Telegram Messenger. As many of you may know, Telegram is one of the most popular instant messaging app and service. It actually services on the most platforms. As you can see on the screen, this Telegram Messenger provides some attractive and interesting animated stickers and emoticons with Lottie animation. And for this application of Android, iOS, Windows version individually adopted our Lottie library in their packaging. Since the property support of Lottie animation wholly depends on Lottie implementation, sometimes but rarely, Lottie animation might not work same as the After Effects designs due to bugs or as it's not supported feature. Thus, to confirm whether the design is compatible with a real device, designers must install the Lottie resources onto real device target so that they can check the result on learning apps. Often, this step is time-consuming or just burdensome for the designers. If designers can figure it out in advance, then the collaborative process would be better. For this reason, we actually suggest the verification steps as you can see on the screen. Firstly, designers can check the feature table of Lottie in the online documentation. In this way, designers can understand which components of After Effects are available on their project. Secondly, once designers finish the VI design based on supporting features, then they can check the preview result on Lottie online viewer. As like the native Lottie animation online viewer, Lottie also provides each one online viewer to check the compatibility more quickly and easily by the developers and designers. Thus, if the preview result is acceptable by the designers, then they can pass the design resource to the developers directly. If the preview result is not acceptable, then they should check the design resources to see whether they broke the compatibility in the design step. Otherwise, they can raise the issue to Lottie developers to fix the bugs. As you may guess, in the most cases, designers may worry about the design confidential issue, meaning leaking the design resources under the development process might be very critical for the project. To deal with this, we actually designed the rlottie online viewer to simulate it on the local machine. That means when you visit rlottie online viewer, it actually installs rlottie WebAssembly binary in your local PC that runs rlottie program. Thus, it won't upload your resources onto any servers, nor transfer them outside. In some projects, design confidential is very sensitive, and we are able to solve this problem by using this method while we are achieving the collaboration between the designers and developers. Dynamic property is a method to customize the Lottie animation. By using this method, we can actually provide customized Lottie animation. At this moment, color, opacity, and transformation are involved in these dynamic properties. As you learned earlier, we could understand the Lottie data keeps a tree-based data structure. Every component node or Lottie data could have its one unique name, key path. Such applications can access a specific node of Lottie animation to change its properties by using this key path on runtime. In fact, this key path is a continuum of fan of names from the root to a specific node. That means this key path name should be discussed and confirmed in advance between the designers and developers so that developers they know which nodes are allowed to customize. Thus, designers can specify the key path name for the component in the After Effects, and developers can use this key path name in the program stack. Practically, this dynamic property is simply used for changing colors, but we can use this for more interesting user interactive transition effect as well. One use case is here. As you can see the demo videos on the screen, the left is the original Lottie animation, and the right is the customized version. Actually, we can make this kind of motion animation by customizing Lottie animation on runtime. Though, as you can guess, it might need some additional logics for overriding, transformation, and importation for Lottie shape nodes. It's definitely better than start from scratch to code this kind of transition effect. And I'd like to introduce one more interesting feature of Lottie in Tizen. Actually, Tizen is going to support adaptive transition for more dynamic transition effect with Lottie animation. The basic concept of this feature is, as you can see on the screen. Actually, we can use Lottie as for place and transition holder. That means we can do mapping any kind of UI object onto Lottie shape nodes while it's keeping the transition effect. Let's assume that applications can replace the Lottie shape node with each one view, image, text, or some controls on runtime. Thus, we can make a previous user interactive transition effect, but more dynamically changeable. This approach allows the designers to design the Lottie animation in a more flexible way that brings applications to have a decision to change transition effect more adaptively on runtime. Clearly, we can apply adaptive transition for this kind of transition effect as well. Left is the original Lottie animation, and right is actually the application bind the view or image onto Lottie shape node on runtime. As you can see, the right side Lottie animation effect. Technically, the 3D transformation is available for this adaptive transition as well. Even we can map or bind some real-time updating object onto Lottie shape node on runtime. All this animation As you can see, the mapping method is available for arbitrary shapes. If you imagine if you implement this kind of a transition effect from the nothing, then you can say it again, it must be horrible. This adaptive transition might be the best of both worlds for the developers and designers. One of the other benefits of this adaptive transition is label. Of course, we can map label or text object onto reserved Lottie shape nodes with Lottie animation. In this way, we can provide the Lottie animation with the specialized label features, such as multi-language for localization or ellipsis, line lengthening, and some others. Okay, it brings us to the end of this presentation. Let's summarize it. At this moment, we are trying more interesting features with Lottie animation. And for this, we are trying to add more features to our Lottie and Tizen UI graphic system. And we are trying more optimization. Obviously, Tizen UX are replacing VI effects with Lottie animation. That means more Samsung devices are coming out using Lottie animation files. Not only mobile phones, but also wearables, smart TVs, home appliances, such as refrigerators, and some others. Through this presentation, I hope you learned what is motion graphics and what is Lottie animation, how to use it in Tizen. And also, I hope you will be able to gain more insight to apply Lottie animation for your future motion graphics UI. Thank you.